now we will look at examples that are equations versus discrete examples. So one thing that we will do, and if we know that an equation is a function, we'll write it in function notation, and it's a way of telling the reader that that is a function. So if I have y equals 3x minus 2, that can actually be written f of x equals 3x minus 2, telling the reader that y is a function of x. So it really emphasizes an input-output concept, and I like to think of functions as like number machines. And so that, and realize that f of x does not mean f times x. It's saying my input value is my domain, or my x's, my output's my y's. And so a domain, it opens the door for alternative definitions, which is really the same definition, but just in a way we can look at an input-output concept. The domain are still all your x values, but we're looking at an equation form. Think of an input of values of all of the entire equation. The range is the output values of the entire equation. And so we can think of these functions as machines. So if I have f of x equals 3x minus 1, it's a linear function, and I take a value and I stick it into the function, that would be part of my domain, my x value. I plug it in, I get 3 times 2 minus 1, and I get f of 2 equals 5, which is 5 is the output, which is a range. So 2, 5 is actually an ordered pair that would satisfy that function. And also you can note that you can plug in any value you want for x. That we call that oftentimes the independent variable. And the output depends on what you plug in. So we consider the output, or the range, is the dependent variable. So now we will look at how do you identify if something, if you're looking at an equation, how do you identify graphically if it's a function or not? So I will show you examples on Desmos here. So if we look at a graph, this is just a graph of y equals x squared. I just do a vertical line test, and if I have no repeating x values, then the graph will never hit, a vertical line will never hit the graph in more than one spot. So here's an example of a function because a vertical line never crosses it in more than one spot. Now it passes the vertical line test is what we would call that. Now what if I change something and I make it something like this, x equals y squared. Now this is going to fail vertical line test. Because now you'll notice that you have repeating x's actually everywhere you go in the graph except for one spot in this case, but you can have repeating x's on this type of example. As long as it hits in more than one spot of vertical line test anywhere on the graph, it fails and it's not a function. So that's one thing that we will do to tell if equation is a function or not. Now some common functions, common equations that are functions always, and what their domains are, we're going to analyze that. Some of the basic functions that we're going to look at are polynomial functions. Polynomial functions are basically functions where you're dealing with polynomial of degree 0, degree 1, degree 2, degree 3, degree 4, so forth. And so f of x equals 3 would just be a constant graph. It's just a flat line graph, and that's a function. It passes the vertical line test. The domains of all of these are always going to be all real numbers. They're continuous. There's no breaks in the graph, and you could, if you draw them, you're always going to have any real number you could plug in is going to give you a real number output for its domain. So if you think of a graph of a constant like this one, we could just do it really quickly. So y equals 3. There's that graph. It's going to go on forever, so you can plug in any value, infinite number of solutions. Or domain is just going to be all real numbers. Now how about an example like a linear equation x minus 2? It's just going to give it a slant or a slope, but you're going to still have all real numbers that you could plug in. Actually a parabola, same thing. Domain is going to graphically be all real numbers. If you think you can plug in any number, it'll cover all x's. Graphically, a cubic will cover all x. It keeps getting wider and wider, and they're continuous. Actually, any polynomial is always, the domain is always all real numbers. Another common one we look at is the absolute value function. And the domain of the absolute value functions, domains of these are always all real numbers. These are the V-shaped graphs, and if you were to graph those, it's always going to cover let's do just the basic absolute value graph, and you see it's a V-shaped. It's going to keep getting wider and wider, and it's continuous. You're going to cover all x's. There's no trouble spots. That's the thing to notice. Now, if you look at the two types that we're going to see that actually give us issues possibly within the domain are rational functions, because you can never have a zero in a denominator, and then also radicals, because if you have to have a non-negative radicand, the thing underneath the root symbol, in order for it to be a real number output, because otherwise if it's negative, we have to pull our I out, it ends up being a complex number. So these are the two types. So basically, when you're asked what the domain is of functions, no, most functions that we look at are going to be all real numbers. But when we look at unusual cases where we have restrictions, like this example I have on here, x plus 1 is in the denominator, so a negative 1 would make that denominator go to 0, so I have to exclude that from my domain. I can't use it. It wouldn't be a real number output. It would be undefined at that point. And then here I'd have to take my radicand, x minus 3, make it greater than or equal to 0, and then solve for x and say, well, x could be anything but 3 to infinity. It can be anything, it can be 3 to infinity, but it cannot be anything less than 3, because then it would make that radicand negative and we'd have a complex number output. It wouldn't be a real number output. So here's the type of examples you'd see. Example number 2 from chapter 12 practice test. If I asked you something like determine the domain of the following, here's a radical function. So I'm going to take the radicand, make it greater than or equal to 0, and solve for x. So x is greater than or equal to negative 3/4 in this case, or negative 3/4, comma, to infinity, including the negative 3/4 square bracket, will be an interval notation way of answering that. That will be the domain of that function. The domain of this function is just all real numbers, because I recognize it's just a polynomial function. There's not going to be any restrictions on that. Now over here I notice, oh, it's a rational function. I have a fraction. I can't have 0 in the denominator. The two numbers that make the denominator go to 0 are negative 2 and 2. You could take that and take the denominator, set it equals 0, and solve for x by square root property or by factoring, and you get negative 2 and positive 2. So that would be an example where all real numbers except exclude those, or you could write an interval notation, but that's a nice quick way of answering it. So that's dealing with the domains and ranges of equation type examples versus the discrete.